Lesson 10.7 is more probability. For this lesson, we are going to be looking at the situation of the fruit bowl and also of the suitcase. To get started, we're going to talk about experimental versus theoretical probabilities, and we're going to practice with this in today's lesson as well. Experimental probabilities has the word, experiment inside of it. So when we talk about experimental probabilities, we are actually going to do the event. So instead of just talking about spinning the spinner like we did in the last lesson, we would actually spin the spinner. And in doing so, we would go ahead and we would collect some data. So spinning our spinner, we would collect our data then. This is different than theoretical probability, which is what we typically are working with. And theoretical probability is what we are thinking about. So theoretical is what we think about. In theory, this is what should happen. It's kind of what we expect to happen when we are given a scenario. And this is simply put when we compare our favorable outcomes to our total outcomes. Theoretical probability is based on facts. So we consider those outcomes and that's about it. In terms of experimental probability, this is not based on facts, but it is rather based on doing our event and collecting our data. For today, in our notes problems, we are going to continue with our theoretical probability and thinking about the favorable outcomes compared to the total outcomes. For our first example, we're going to be talking about a fruit bowl. We have 7 oranges in our fruit bowl and 6 apples. One of the first things I would always suggest you do is to go ahead and add these together, which does give us 13, so that we know how many potential outcomes we are talking about. In step number 1, the first part, we're going to talk about single event probability. Single event just means that we are picking one. So if I'm going to try and pick an orange, there are 7 oranges in my fruit bowl, and that's compared to 13 total pieces of fruit in the bowl. There's nothing I can do to reduce this since 13 is a prime number. The probability that I pick an apple, there are 6 apples in the fruit bowl, and there are 13 total pieces of fruit. So the probability is 6 out of 13. Single event is the most simple probability that you can actually encounter. When you take a look at the next page, page 13 in your notes packet, we are now going to talk about 2 different scenarios that can happen when we're picking more than one piece of fruit. Again, we're still talking about the scenario where we have 7 oranges and 6 apples for a total of 13 pieces of fruit. In our first scenario here, we're going to talk about compound events, which is 2 things that happen with replacement. So when I say with replacement, it means you're going to make your first selection. You're going to look at it, say, oh, nope, I changed my mind. Put it back in the fruit bowl before you make your second selection. So our probability of selecting an orange and then an apple is going to work like this. The probability that I pick an orange is 7 out of 13. I get my orange, I look at my orange and I say, you know what, I changed my mind. You put it back in the fruit bowl. So now instead of that piece being gone, it's right back in. So you're back to having 13 possible pieces of fruit to choose from. You decide now that you want an apple. So that's 6 out of 13. Just like we saw with our basic events before, we're going to be multiplying these because there's a total of 13 times 13 possible outcomes. So we go ahead and we multiply. 7 times 6 is 42, and 13 times 13 is 169. That tells me that the probability that I pick an orange, put it back into the basket, and then pick an apple is 42 out of 169. You can change that into a decimal and into a fraction, and you would actually find out that that's going to be about 25% chance. Not a decimal and a fraction. We already have the fraction, but a decimal and a percent. So that percent would be about 25% chance then. I'm going to go ahead and figure out the probability that I first select an orange. There are 7 oranges out of 13 pieces of fruit. I look at the orange, I say, I don't really want this one. I changed my mind, so I put it back in. And then I decide, yeah, I actually did really want that orange. So now I'm going to grab another orange, which is 7 out of 13. Again, multiplying across, I get 49 out of 169. And just out of curiosity's sake, that gives us a probability of about 29%. I feel like sometimes changing over to that percent allows us to get a better idea of what's actually happening. For our last example, we're going to pick an apple, which is 6 out of 13. We're going to look at our apple and say, nah, I don't really want that. You put it back in. And then you're going to go ahead and pick another apple because you decide you did want it. So there's 6 apples still in there out of 13 total, for a total probability of 36 out of 169, which would give you a probability of about 21% then. So real quickly, I'm just changing this fraction to a decimal and then moving that decimal point over. That's one of the examples that you can do. Now, what happens if you're really hungry? So you go to the apple and orange fruit basket with the 13 pieces in it, and instead you decide, I'm going to eat this, and then you go back and get another one. So when that happens, the probability that we pick an orange on our first pick is 7 out of 13. I have eaten that orange. So now when I go back to the fruit basket, there are only 12 pieces of fruit that are left in there because I already took out that orange that I got. One of the things you need to understand is that if you picked the orange and you're trying to pick the orange, you are going to assume in probability that you actually got that orange. So you got the orange, and now there's only 12 pieces of fruit in there. When you go to pick your apple, there are still 6 apples that are in there because that's what you started with, and you haven't touched the apples yet. And then you would go ahead and you would multiply. You can simplify before you multiply. So 6 divided by 6 is 1. 12 divided by 6 is 2. That gives me 7 over 26. And again, you can change that over to a percent if that makes you understand it a little bit better. For the next one, we're going to go for an orange and then another orange. On my first pick for an orange, there are 7 of them out of 13. When I go back to the fruit bowl, there are now only 12 in there. And because I already was trying to get an orange, when I go back for the second one, guess what? There are now not 7, but there are only 6 oranges that are in there. So again, I can reduce. This becomes a 1, that becomes a 2, and I get 7 out of 26 for the probability of this one as well. So this process carries over with our suitcase example. We have in our suitcase 3 blue, 2 black, 1 purple, and 1 red shirt. So we're going to just figure out real quickly here. 3 plus 2 is 5, 6, 7. So we have a total of 7. The probability that I pick out a purple shirt is just 1 out of 7. The probability that I pick a black shirt is 2 out of 7. In my first set of examples, I'm going to do compound events with replacement. So this is where I change my mind. So I put it back into the suitcase. There are still 7 pieces in there. On my first pick, I want to get blue. There are 3 blue shirts out of 7. I changed my mind. I put it back in. Now I'm trying to get black. There are 2 black shirts, but there are still 7 in the suitcase. 3 times 2 is 6. 7 times 7 is 49. In the next example, I want red and then blue. The probability that I pick out red is 1 out of 7. I change my mind, put it back in there, and when I go back, there are 3 blues, so I do times 3 out of 7. 1 times 3 is 3, 7 times 7 is 49. For the last example, I want to get a purple and then a purple. So there was 1 purple shirt in there. I change my mind, put it back in the suitcase and say, nah, you know what? I actually do want that purple shirt. So I do 1 out of 7, and the probability that I'm able to pick that again is 1 out of 49, or just about 2% there. So those are compound events with replacement. The final piece to this is compound events without replacement. So let's pretend in this scenario here that I am going to take out the shirt, wear it, and then pick another colored shirt here. So just kind of to help us out so I don't have to flip back and forth, we have 3 blue, 2 black, 1 purple, and 1 red. So I'm just going to write those out up here, still for a total of 7 different shirts. So when I go to pick my blue shirt, there are 3 blues out of 7 shirts. I've worn the shirt, so now I'm down to only 6 shirts in my suitcase. When I go to pick out a black, there are 2 of those still in there. I can reduce. This becomes a 1, this will become a 2, and you'll notice my 2's can actually cancel, and I end up with 1/7. Obviously, you could be using your calculator for these, but these are such simple multiplication problems that you should be able to multiply these fractions. On my next round, I'm going to start over with my suitcase. I want to pick a red and then a blue. Probability that I pick a red is 1 out of 7. Because I've taken that red shirt out and worn it, I'm down to only 6 in my suitcase. When I go back to pick out a blue, there are 3 of those that are in there. I can reduce my 3 and my 6. This becomes a 1 and this becomes a 2. So multiplying across, I get 1/14. On my last pick, I'm trying to get a purple and then a purple. So when I go to my suitcase, I have 1 purple shirt out of 7 shirts in my suitcase. I wear the purple shirt, so I'm down to only 6 shirts in my suitcase. And I go back in for another purple shirt. But guess what? I only packed 1. So since I already took that 1 out, I have 0 purple shirts to pick from. Anytime I multiply by 0, my probability is 0. So it's not possible for me to select 2 different purple shirts here. Final piece for this lesson is a quick little intro, and we're going to pick this up in the next lesson as well when we talk about independent versus dependent events. Independent is 2 or more events, and independent events have no impact on the other. So for example, in our last lesson when we saw spinning the spinner and then doing something, or rolling a dice and then rolling another dice, they have no impact on each other. The other scenario that we see these is when we have replacement. So we saw examples like that today when we picked out the shirt from our suitcase and then put it back into the suitcase. It didn't change the scenario. Other examples would be to roll a die, to flip a coin, or spin a spinner. Those things have no impact on each other, and it's not like the spinner changes after you've actually spun it. For dependent events, we also have 2 or more events. Dependent events, though, the first event affects the following events. So whatever happens on that first pick does in fact affect the following events. In our notes today, we saw these examples as ones that were called without replacement, because once you took the shirt out of the suitcase was now different in that it had less shirts in it and the suitcase scenario was changed. So that's the difference between dependent and independent events.